Today we're going to look at more differentiability and continuity, and then we're going to introduce our basic differentiation rules. Yesterday we ended, our definition of a derivative was, so f prime of x equals the limit as delta x goes to 0, or in some books it'll say h, of f of x plus delta x minus f of x, all divided by delta x. And we worked with that. Now, we're going to look at an alternate form, okay, f prime of c, as instead of it going to 0, as the limit goes to c of f of x minus f of c over x minus c, provided the limit exists. Remember, in order for a big limit to exist, the limits from the left and right must exist and be equal. All right, moving right along. If the limit from the left does not equal the limit from the right, then the big limit does not exist. All right, so we've taken a look at that before. Since our definition of a derivative depends on the fact that the limit exists, if I can't do the limit, I can't do the derivative. Also remember the conditions for continuity. It says if the limit of a function doesn't exist at a point, the function is not continuous at that point. Therefore, continuity and differentiability are closely related. And this is because of limits. So basically what this is saying is if it's not continuous at a point, it's not going to be differentiable at a point. You're not going to be able to find the slope of that tangent line. All right. And if a function is not continuous at a point x equals c, then it is not differentiable at that point x equals c. And that's what I was just stating. Now, let's look at this. And we took a look at the step function the other day, greatest integer function. This function is not continuous at x equals 1. So look right here, x equals 1, it's not continuous so because I jumped. However, like at x equals 1/2, it is continuous. Okay, but we're looking at x equals 1. So since right here this is not continuous, what it's stating is that at x equals 1, it's not going to be differentiable. Same thing at x equals 2. There's a jump here. So therefore, it's not going to be differentiable there. All right, it will be differentiable anywhere in between like 0 and 1, but just not there. So what if the function is continuous at x equals c? Does that mean it is differentiable at x equals c? So let's look at this right here. We're looking at the absolute value of x minus 2. You were first introduced this in Math 3. Okay, I have a graph here. All right. The function is continuous at x equals 2. Here's that point right there. I don't have to pick up my pencil. All right, it is continuous, but is it differentiable? Okay, so does continuity always mean differentiability? All right, and that's what we're trying to prove here. So we took that alternate, all right, that alternate definition of a derivative, f prime of 2 equals the limit as x goes to 2 of f of x minus f of 2 over x minus 2. Okay, so what we did was you got to do the limit from the right and the limit from the left. All right, f of x is just the function right here. Okay, absolute value of x minus 2, absolute value of x minus 2, and then we do 2 minus 2. Okay, as it comes from the right, think about it. They're all like the positive values, say 3, 4, 5, 6. Let's think about this for a second. Okay, what does it go to? So this will always be positive on top, and as long as it's 3, 4, 5, 6, 7, 8 going up, it'll always be positive on bottom, so it equals 1. All right, let's look at this one. Now, this is 2 from the left. That means the values are 1, 0, -1, -2, and so forth. Now again, the top is always going to be positive, but think about the bottom. If it's 1, it's -1. If it's 0, it's -2. If it's -1, it's -3, and so forth. That will always be negative down here. So positive divided by negative, and it's the same thing, is -1. Are these equal? All right, no. So the limit from the right is not equal to the limit from the left, so therefore, the derivative at 2 does not exist. And we could say something here. Notice what actually happens here. This isn't just a nice little curve right here. This is called a sharp turn. What happens is a function is not differentiable at a point at which its graph has a sharp turn. Okay, now, every now and then they may be, but for the most part, especially like the absolute value functions, they have a sharp turn right here, that V shape, okay, at that vertex. Usually it is not differentiable right there. So let's take a look at some others. So let's look at this right here, okay? Function is continuous at x equals 0. Is it differentiable? Okay, so let's go look at it. All right, so what we're going to do is we're going to use that alternate definition. Remember, it was f prime of c equals the limit as x goes to c of f of x minus f of c and then x minus c. All right, so here we go. We're going to find f prime of 0, or c value 0, as the limit as x goes to 0 of f of x. I'm going to go ahead and plug in x to the 1/3 minus, okay, it's going to be f of 0. Well, think about it. When I plug 0 into here, what is it? It's 0. And then it's x minus 0. Well, this comes out to be the limit as x approaches 0 of x to the 1/3 over x. And that's to the first. Now think about what you can do with your exponents. Okay, you can subtract them. And what I end up with is x to the 2/3 on the bottom. Now let's think about this. As this goes to 0, now at 0 it's undefined, but let's think. As this gets closer and closer to 0, all right, what does it go to? Think about it for a second. Think about it, it's going from 1 to like 3/4 to 1/2 and so forth. If we want to graph it, we can. It's 1 divided by x raised to the 2/3. All right, zoom 6, and if we look as x goes to 0, all right, we notice both of these actually end up going up. And this is a little misleading because it looks like it stops, but it doesn't. It keeps going up forever, so it keeps going off to infinity. But wait a minute, this doesn't make sense. Okay, because a derivative is supposed to represent the slope of a tangent line, and we can't have a slope of infinity. So infinity means there is a vertical tangent line at x equals 0. Therefore, no slope. Hence, no derivative. All right. So let's do this again. All right, at these values. Okay, so we're going to do f prime of 2. And what we're doing is we're saying f of x minus f of 2. And I meant to put the limit as x goes to 2 of x minus 2. So this is the limit as x approaches 2 of, well, f of x is just this x squared minus 1 minus f of 2 is when I plug this in here. 2 squared is 4 minus 1 is 3. All right, so let's reduce this. The limit as x approaches 2. Okay, that's going to make x squared minus 4, but remember, that can get factored into x plus 2, x minus 2. Okay, and the x minus 2's can cancel out. So we're left with the limit as x approaches 2 of x plus 2. Well, here, as this goes to 2, I can just plug it in. 2 plus 2 is 4. All right, so the derivative This is the derivative at the point of 2. Yesterday we actually found the actual derivative that we can plug in x into. This time we're already plugging in that x value. All right, so let's do it again here. We want to find f prime of negative 2. The limit as x approaches negative 2. We're going to say f of x minus f of negative 2 over x minus 2. F of x is, keep with limit notation. When I plug negative 2 into there, I'm going to go ahead and do this. Negative 2 cubed plus 2 times negative 2 squared plus 1. So that's negative 8. That's going to be positive 8 plus 1. All right, so that just gives me 1 right there. And I messed up right here because it's supposed to be negative 2, so that turns into a plus right there. All right, here you'll notice the 1's cancel, and an x squared actually factors out. And then you'll notice that your x plus 2's cancel. So when I plug in negative 2 into x squared, I get positive 4 again. So the slope of the tangent line at x equals negative 2 is 4. All right, moving right along. Let's do this again. Okay, so here to find f prime of 1, we want to do the limit as x approaches 1 of f of x minus f of 1 over x minus 1. All right, so the limit as x approaches 1 of x minus 1 to the 2/3. All right, minus, now when I plug 1 in there, I get 0. Okay, well here, think about this for a second. This is x minus 1, but it's to the 2/3. This is x minus 1, but this is to the first power. So what can I do with that? I can subtract them, and I'm left with 1 over x minus 1 to the 1/3. If you want to look at this on a graph, you can. All right, but let's think about this for a second. As I plug 1 into here, it becomes 0. All right, and right here, the limit does not exist. Okay, so what that means is it is not differentiable at x equals 1. All right, so enough about that. Let's get to our basic differentiation rules. You're probably not going to use this all that often because you're going to memorize these rules that we go over in just a second. All right, so our basic rules. Now, as far as notation, you've seen this before, but I wanted to reiterate it. The function is f of x. The first derivative is f prime of x. Or the second derivative is f double prime, and we notate that with 2 tick marks. And then you see the same thing. Now for y, we got y prime, or we can say dy over dx. For the second derivative, it's y double prime, or it can be d squared y over dx squared for the second derivative. So you're going to see those pop up all year long. Now, as far as the basic rules, make sure you pay attention to these rules. So the derivative of a constant is 0. Okay, so we say d of dx of c equals 0. And as an example, okay, y equals 7. All right, therefore, y prime, what does that equal? 0. Or if I had f of x equals 3, then f prime of x equals 0. So just remember that the derivative of a constant is 0. Okay, our next rule is called the power rule. What this states is, say I have a y equals x to the n. Then our derivative equals, what we do is we take this exponent and we multiply it out in front, and then I drop the exponent by 1. All right, so this is what this looks like as an example. Say f of x equals x to the 5th. So f prime of x is going to be, I'm going to multiply the front by 5, and then x, and then I drop the exponent by 1, so that's to the 4th power. All right, let's say g of x equals x to the 1/2. All right, so g prime of x, I'm going to multiply the front by 1/2, and then x, and then I drop this by 1. Well, 1/2 minus 1 is negative 1/2. I'm okay if you leave it like that. Now, do realize if you could run across multiple choice, they will make you simplify it. This is the same thing as 1 over 2 x to the 1/2, which is the same as 2 square root of x. So just recall your rational exponents. All right, let's say g of x equals x. All right, so g prime of x in this case. Let's think about it. The exponent here is 1, so I'm going to multiply the front by 1, and I drop the exponent by 0, but what is anything to the 0 power? 1. So really, it's just that coefficient of 1. All right, y equals negative 5x to the negative 3. So dy dx equals, all right, here what we're going to do is multiply the negative 3 times the negative 5 to get positive 15. And then you subtract 1 from that, and you get negative 4. Again, I'm okay for you to leave it like that, but some answers may come across like that, especially if it's multiple choice. So that's the power rule right there. Now the next one are 2 trig things that you need to have memorized. Okay, sine and cosine. The derivative of sine x. The derivative of sine x is cosine x. And the derivative of cosine x is negative sine x. Memorize those. Okay, notice that this one is negative where that one is not. So here's an example. Let's say y equals 2 sine x. All right, we're going to keep that constant out in front, okay, of 2. But what's the derivative of sine x? It's cosine x. Or let's look at this one. Y equals cosine x over 2. Now you're welcome to switch this so it's 1/2 cosine x. All right, but y prime equals, all right, we're going to keep the constant. We just multiply it by the derivative of cosine x. That's going to be negative sine x. So this really makes negative 1/2 sine x. Or you can say negative sine x over 2. All right, so let's put this together and let's do a couple. All right, so y equals 2 over x. Pause the video to see if you can do it on your own. Okay, now anytime it's in the denominator, I like to raise it up so you have a negative exponent. So now to find y prime, you multiply 2 times negative 1, which is negative 2, and then you drop that by 1. So negative 1 minus 1 is negative 2. You're welcome to leave your answer like that, or you can switch it. Okay, for, let's see, f of t equals 4t squared over 5. Okay, so let's find f prime of t. Okay, you got this 4/5 out there. Keep that. You're going to times it by the exponent of 2, and then you're going to drop that exponent. So this makes 8/5 t. All right, number 3. Y equals 2 square root of x. Anytime you have a radical, change that to a rational exponent. So this is 2x to the 1/2. Remember, your index is 2, the exponent's 1, so 1 over 2. All right, so y prime is, I'm going to multiply the 2 times the exponent of 1/2, and then I drop the exponent, so that makes -1. I drop it by 1, so it's -1/2. All right, if I want to clean this up, these divide out. I can leave it like this, or I can write it like that, 1 over square root of x, either way. Okay, number 4. Okay, y equals 1 over 2 cube root of x squared. Again, I would change this because I have a radical to a rational exponent before doing anything. Now there's a 1/2 out there, and this is going to be times 2x to the, you're saying 2/3, but since it's down low, I'm going to bring it up and it's going to be negative. Okay, so now dy dx. All right, I'm going to have the 1/2 and I'll multiply it by that exponent, -2/3. All right, and then I drop that by 1. So think about subtracting 1 from this. Okay, remember that's 1 right there, so it's -5/3. So this is, the 2's cancel, I'm left with negative, so -1/3 x to the -5/3. And I honestly would just leave it like that. I wouldn't really do anything with it unless you want to put that x to the 5/3 down low. I wouldn't change it back to a radical. Okay, here's another one. Y equals -3x over 2. This is the same thing as -3/2 times x. All right, so y prime. Okay, this is a 1. So 1 times that is -3/2. And then when I drop that, that becomes 0. Well, remember, anything to the 0 power is just 1. All right. Here's another one for you. Now I would go ahead and cube this denominator, so that's 8x cubed, and then I would bring that up so it's x to the -3. So when I find dy dx, I'm saying 5/8 times the exponent of -3, and then I drop that by 1, so it's -4. So when I clean it up, it's -15/8, and I can take the x to the 4th and put it down low. All right, f of x equals x cubed minus 4x plus 5. So here we go. We're actually applying the power rule several times. Okay, we're bringing the 3 out in front and dropping the exponent by 1. Minus, okay, here the exponent's 1, so 1 times -4 is -4, and then that x no longer exists there. And then what's the derivative of a constant? 0. So here's our derivative. All right, g of x equals -x to the 4th over 2 plus 3x to the 3rd minus 2x. Okay, so here goes g prime of x. All right, that's a -1/2 right there. I'm going to times it by the 4 and then drop this by 1. Plus, I'm going to take that 3 and multiply it by the 3 right there and then drop that by 1. Minus, okay, this is a 1 right here. 1 times -2 is -2. When I drop it by 1, 0, so it no longer exists. Okay, so here we go. If I clean this up, this is going to be -2x cubed plus 9x squared minus 2. And then one more. Y equals x plus cosine x. All right, so this time we actually have a trig in there. So what's the derivative of x? You should have 1. Plus the derivative of cosine x is -sine x. And there's its derivative. So make sure you have these basic differentiation rules memorized. Okay, it'll make finding the derivative a lot quicker. All right, as we go along, and you will use them throughout calculus the entire year.